All right, welcome back. Today we're going to be talking about maximization and minimization problems, also known as optimization problems. One of the most common applications in calculus. It fits right in what we were doing in chapter 4 or unit 4. We're going to use the first derivative test basically in order to find out how to make things super big, super small, given some constraints. The procedure is right here. We're going to choose some variables or draw a labeled figure. Very helpful step. Write a primary equation, making sure we isolate whatever is to be maximized or minimized. Rewrite it with only one variable on each side. This might require a secondary equation. Then we're going to find the domain. Basically, what's the biggest number, what's the smallest number our input could be. And then take the derivative, find critical numbers, make a number line. That's the only real calculus step. That's all covered in Unit 4, which should be very familiar for you. 3, 2, 1, go. All right, so we're going to try to answer this with a complete sentence at the end. It's always an important step. So here we have a box with no lid. The blue sides are the sides. That's supposed to be empty. The bottom is there. We have 48 centimeters square of material. If the box is to have a square base, find the dimensions that produce the maximum volume. Well, first thing I notice is this. First sentence, where we have a 48 centimeters square of material. Square centimeters, or square length units in general, are only ever used for area. So this is talking about the surface area of the box. This 48 centimeters square. Because I see centimeter squared, I know that's talking about the surface area. So that's a fixed quantity. That will actually end up being a constraint, or the secondary equation. What are we trying to maximize? What are we trying to minimize? That's always the primary equation. But before any of that, we can consider the first step, which was to choose variables or draw a labeled figure. Since I already have the figure here, let's choose some variables. So one choice of variables might be your standard. We call this the length, we could call this the width, we could call this the height of that box. But we notice here that we have a square base. That means these two sides are the same. So I'm going to say the width is x as well as the length. And we can change this to y or not, depending if you want. Find the dimensions that produce the maximum volume. So now we're finally going to write our primary equation. This is technically step 2. We're trying to maximize the volume. So what would the volume of a box that looks like this be? Well, the volume of this box would be length, x, times the width, x, times the height, h. So that would be x times x, or x squared, times h. And this would be my primary equation. Again, that's primary equation because it's what I'm trying to maximize or minimize. But maximize in this case, for sure. So now we look at step 3, which is to say rewrite with only one variable on both sides. As you might have noticed, we have v, one variable on the left side, so the only side with two variables is over here. That's what we mean by one variable on both sides. We'd like to get rid of either x or h and only have an equation that has h on one side and v on the other, or x on one side and v on the other. V on the left, x on the right, v on the left, h on the right. So that brings us to step 3, a secondary equation. And that's where this surface area is going to come in. So I know the surface area of this box would be the bottom side, which is again x times x, which is x squared, plus each face. So this front face, or the back face, I don't know however you think about it, is x times h. And then the side face would be x times h. That would match, that would match. So really we have 4 faces, each with an area of xh. And if you add up all of the surfaces of this box, you would get the surface area, which is 48. So that's my secondary equation. Now, when I try to solve this equation, I'm going to think about which variable would be easier to replace in my primary equation. X, if I wanted to replace x in this equation, I would have to square whatever's left, which probably won't be the most convenient thing. So instead, I'm going to try to replace h. Since I want to replace h in the primary equation, I'm going to look over here and try to solve for h. An alternative strategy would be to look at this equation and think about which one's easier to solve for in this equation. Is it easier to solve for x here or solve for h? And we come to the same conclusion, it's much easier to solve for h. H is already basically by itself. To solve for x, you'd have to do something akin to the quadratic equation, or the quadratic formula. So here we go. We're going to solve for h, subtract x from both sides, get 48 minus x squared, divide both sides by 4x, you would get h equals 48 minus x squared over x. And we are going to substitute this back over here to get v equals x squared times 48 minus x squared over x. I'm sorry, I forgot a 4. And we simplify this pink equation to x times 48 minus x squared over 4, canceling out the x's, or dividing out the x's. We can further simplify it by basically dividing each of these by 4 and distributing to get 12x, that's 48 divided by 4 times x, minus 1/4 x cubed. And that's the end of step 3, believe it or not. Step 4 is about finding the domain. Now, if I want to define the domain here, I'm basically thinking about what is the largest input I could have and what is the smallest input I could have here. It's not immediately clear. If you're good at the chapter 1, the pre-calculus stuff, you would notice that this is a polynomial equation, and so it has no real errors. But if you trace it back to before we started simplifying, which if you're really good at chapter 1 or pre-calculus stuff, you know we have to consider domain before we simplify. The domain is really coming from this issue. The domain comes from how we got rid of one of our variables. So when I'm asking what is the largest x could be and what is the smallest x could be, I have to consider it through this lens. Because again, looking here, it's not clear we have a largest or smallest value. So a useful exercise sometimes is thinking about negatives coming in from the left. Could x be -1? Could we have a side length of this box where x was -1? Since this is a real world box, the answer should simply be no. And the same would be true for any negative number. And this is why it's hard. This is where you have to actually use your real world knowledge. So we know x could be not negative. Could x be 0 is my next question. We've ruled out all the negative numbers. Could x be 0? And this is a little harder to see. A lot of students end up saying x cannot be 0 because then we would have nothing here, and the box, quote unquote, would be a straight line. That's one reason. We would have no volume. But specifically, we also have a deeper algebraic issue right here that if x were 0, we would have no surface area, which is similar. Also, you could look here. If we have x equals 0, we would be dividing by 0, and h would be undefined. So all of those things together tell me that x can't be 0. What about 1/2? What about 1? All the other numbers after 0 are okay, up to a point. So 0 will be our lower bound. We have 0 just barely bigger than. It has to be bigger than 0. It cannot be equal to 0. A lot of thought went into that 0. Be careful. You can make a note for yourself. X equals 0. X less than or equal to 0 would break the box. Right? All those numbers would make this box non-existent. Now, is there a number x cannot be larger than? Is there an upper limit on x's size? So literally what I think of is, let's go really big. Could x be 1,000,000? Now this won't always work for practical purposes, but it'll work for every problem on the AP test. Could x be 1,000,000? Well, what would happen? Most students end up saying yes, again, because they're fixed on the simplified versions, and they see no problem with that. But again, look at this equation. If x were 1,000,000, our denominator would be fine. But what about our numerator? Our numerator would be 48 minus a really, really big number. So our numerator would be negative. And we just talked about how side lengths can't be negative. If you really start thinking critically, you might be able to use the same argument we had over here to find the exact upper bound. So if you want to pause the video and try to do that, go ahead. 3, 2, 1. All right, here we go. The exact argument we used over here would work here. H has to be not 0. H has to be positive also. So if we're thinking about h having to be bigger than 0, then x has to be less than the square root of 48. Because if x were bigger than the square root of 48, then h would be less than 0 or equal. That's why x has to be less than root 48. And this really will matter for getting a nice answer here. A lot of students, when they first tried, write 48, which certainly x has to be smaller than 48, but it actually could be a lot smaller than root 48. Well, sorry, a lot smaller than 48. Up to root 48 is the maximum. 48, root 48 squared is 48, and that's where we would get 0. All right, it's time for some calculus, finally. So step 5 is all about finally taking the derivative. So if I take the derivative of this pink equation here, I would get v prime, the derivative of v, would be 12 minus 3/4 x squared. We're looking for critical numbers. Looking for critical numbers, I'm setting v prime equal to 0. 0 equals 12 minus 3/4 x squared. 3/4 x squared equals 12. x squared equals 16, x equals 4 or negative 4. This is really killing a lot of students' grades. You have to remember to have both the positive and the negative option. And it's useful to write it this way instead of the common plus or minus notation, because this will remind you to check if both values are in our domain. And if you consider carefully, you will notice that negative 4 would not be a possible side length here. So we're left with one critical number, x equals 4. Trying to shrink a lot of stuff. Bear with me. Okay, there we go. So 3, 2, 1. Here we go. So we would make a number line to test that critical number. Now, using our domain knowledge, our number line should be restricted from 0 up to and not including root 48. We can put 4 right in the middle of the number line. It doesn't really matter. Between 0 and 4, we're trying to check for the sign of v prime. Between 0 and 4, we could test 1. V prime would be positive. After 4, a number like 5, a number like 6, any number you want, a number like 8 would be easier to do math with. You would find out it was negative. You could also use the fact that 4 wasn't even odd 0, but that's a little harder. You don't need to go that hard. So we see that v prime is positive, so v is increasing, and then v is decreasing. Since v prime is positive, volume will be increasing as x gets toward 4, then volume will be decreasing after 4. We will use our techniques one more time to find the actual dimensions. If x equals 4, that implies that h would have to be 48 minus 4 squared over 4 times 4, or also 4 squared. And again, that's coming all the way from over there, in case you can't tell from the structure. And if you simplify that correctly, you get 48 minus 16, 32, divided by 16, h equals 2. Now for our final sentence, something like this: the volume would be maximized when the dimensions are 4 centimeters by 4 centimeters by 2 centimeters. That's it for this problem. A good problem to try out right now would be probably number 3 or number 2 in the assignment. We're just going to keep going in this video though. So if you want to pause and try a problem 2 or 3 would be good. 3, 2, 1, here we go. The product of two positive numbers is 288. Find the two numbers so that the sum of the first plus twice the second is as small as possible. So what I notice right away is that I have no picture, and there's no real picture we can get for just two numbers. So let's just label a variable. So step 1 would be something like, okay, let's say x equals the first number, and y equals the second number. Step 2 is to look for our primary equation. So what do we want to maximize or minimize? Well, it doesn't use the words maximize or minimize, but it does say the synonym or the synonymous phrase, small as possible. Now, usually students are short-sighted and they only say, oh, the second is as small as possible. So all I want to do is minimize the second number. But that's wrong. What do we want to be as small as possible? The sum. The sum of twice the first plus the second is as small as possible. We want all of this to be as small as possible. And it's really easy to overlook that, so please be careful. So we want to minimize, we can use M or something like that. S is not ideal, S kind of looks like 5. We want to minimize the sum of twice the first plus the second. And that'll be our primary equation. Now we think about our secondary equation, also known as the constraint equation. The constraint equation in this case is this first sentence. The product of two positive numbers is 288. So the constraint equation says the product, multiplying them, has to be 288. Now we can think about what we want to solve for here. In this case, unlike the first one, doesn't really matter. It's kind of easy peasy no matter what we do. Let's do it with y. Let's just keep everything with x for today. So we're going to replace y in this equation. So we're going to look at our secondary equation and solve for y. Since I want to replace y up here, I want to solve for y here. So y equals 288 over x. And combining this one and this one gives me my new equation that I'm interested in, which is m equals 2x plus 288 over x. Let's consider the domain for a second. The domain, again, we look at here. Domain from here. We can also think of the natural setting here. So is there a number x can't, is there a smallest value of x? Can x be negative? If you think about it, no. X certainly cannot be negative. Why? Well, the product of two positive numbers. Since x has to be positive, we have 0 as a lower bound, and we can't be 0 either. It's commonly overlooked that 0 cannot be positive. It's neither positive nor is it negative. So if I say I want a positive number, I'm excluding 0. If I say I want a negative number, I am excluding 0. If I say I want a non-negative number, that's when 0 can come in. But positive and negative mean not 0. Positive means not 0. Anyway, is there a largest number for x? Could x be 1 million? Usually students say no. X can't be 1 million. If x was 1 million, then y would be too small. But would it be? Really, would it be? If x was 1 million, y would be 288 divided by 1 million. That's still some positive number. It's a really tiny positive number, but it is a positive number. Huh. A lot of students say x can't be 288. But if x was 288, y would just be 288 divided by 288, which would just be 1. And if you keep thinking like this, you keep thinking along these lines, you see there is no largest number. So we're stuck with infinity. I don't like that. Infinity. So we're going to go with infinity as our largest number. And again, that's not really our largest number. That's just for our domain. It's a symbol that means we can't go past it. So now step 5, also known as the calculus step. We take the derivative of both sides. Before I take the derivative, you might want to think about, ooh, I don't like doing the derivative of this. I certainly don't want to use the quotient rule here. That would be overkill. It'd be far easier to rewrite this, which I will do right now. Using a negative power, it's much better to rewrite it than to use the quotient rule. It's much more error prone. Whenever one of your things is a constant, you should not be using the quotient rule. You should try rewriting it to make a coefficient and a power. M prime would be 2 minus 288 x to the negative 2. Since we actually want to use this to find critical numbers, I will rewrite again, saying that's 2 minus, and now I'm reversing the process. I'm rewriting this so that I don't have a negative exponent, 288 divided by x squared. Common algebra error is to try to divide this 2 by x squared also. The x is only attached to the 288. Please make sure you reflect that here. Looking for critical numbers, m prime equals 0, 0 equals 2 minus 288 over x squared, 288 over x squared equals 2, 288 equals 2x squared, x squared equals 144, and we'll make it x equals 12 or negative 12. Look at the domain. Look at the domain. Oh wait, we can't have negative numbers. So that gets crossed out. And those are our only critical numbers. Our only critical number is x equals 12. I will make a number line. Ending at nowhere, infinity. You could just leave that stuff off. In fact, I will. And put 12 right in the middle. This will reflect the fact that we go on forever. An arrow. I'm going to shrink everything so I can have room for my labels. It's going to make the highlighting look ugly. Sorry, sorry, sorry. That's my m prime number line. Trying a number between 0 and 12, we would find that m prime would be very negative. Trying a number after 12, don't overthink it. You can try any number. You can try a million. 288 divided by a million squared is a tiny, tiny number. They'll surely get positive. You can try any number that's convenient. Don't feel fixed to try like 13. 288 over 169, it's definitely less than 2, but I only know that because I know all the numbers over here have to make it less than 2. Try whatever number you want. Use your brain. This is the reverse situation from before. If that's our m prime, our m graph would look like a decreasing graph. Since m prime is negative, m is decreasing. Since m prime is positive, m is increasing. That means 12 is the location of a relative minimum. Because of the shape of the graph and the domain we're on, 12 must be the absolute minimum. So we'll use x equals 12, y equals 288 over 12. What you don't have to know, you could leave 288 over 12, but it is in fact 24. And now when we go to write our final answer, careful Do not say the sum is minimized when x equals 12. Sometimes they will not accept that. I certainly won't on my tests. The sum is minimized when, don't use your label, go back to their labels. When the first number is 12, and that's again where this comes in handy. The fact that we told our reader what the first number was, it helped us remind ourselves. And the second number is 24. Or 288 over 12, it's up to you. You should now be able to do the whole assignment on page 82. Good luck. Please let me know if you need any more help. Have a great day or a great night. Bye for now.